Recording started.
Okay, we're doing problem number 6 for section 10.2. So we're asked to sketch the curve represented by the parametric equations, and I'm going to use this wind plot, which I'm going to post on Blackboard so you can get access to it. But it's just a different program than we're used to dealing with it, and partially we're using it because, well, mainly we're using it because it allows us to do parametric equations. And it's a little easier to see than the graphing calculator, but if you're using your graphing calculator, that's fine as well. And then it asks to write the corresponding rectangular equation by eliminating the parameter. So let's go ahead and eliminate the parameter first. The one thing you have to do is you have to be careful when you eliminate the parameter that you are reflecting any change in the domain. So what you can see from the original equation that t can go from negative infinity to positive infinity. There's no reason why it can't. But you do notice that x and y must be greater than or equal to 0. Actually, y is actually going to be greater than or equal to 1. So let's say x, because anytime you have a negative number here, you're still going to get a positive x. So x is greater than or equal to 0, and y is going to be greater than or equal to 1. So when we eliminate the parameter, we solve for t. So we'd have t squared is x over 2. Take the square root, so you get t is equal to plus or minus the square root of x over 2. So we solve for t, and then you substitute it back into the second equation. So we get y is equal to plus or minus the square root of x squared to the 4th power plus 1. And so whether this is a positive or negative, you're always going to get a positive quantity because it's an even power. So what we'd end up with is the square root of x to the 4th power is going to be x squared, and the square root of 1 over 2, 1 over the square root of 2 is square that, you get 1 over 2, and you square it again, you get 4. So you get x squared plus 4, x squared over 4 plus 1. So this is the equation for a parabola which has a center at x equals 0, y equals 1. And it's stretched so that it's going to be flatter than a parabola, normal parabola. So anyway, that's the corresponding xy formula. So let's plot this parameter using this equation using parametric equations. So I have to open up the graphing program, and I'll describe this to you. So let me actually start all over again, because you'll open it up and it'll look like this. So you go up to Window, and we choose 2 dimensions because we're just dealing with a 2-dimensional equation. So you have x and y coordinate system. And you go to Equation, and you can pick Parametric Equation. So we have, it says f of t and g of t, which x is f of t and y is g of t. So it shows it right there. So according to our problem, we have 2t squared, and we have t to the 4th plus 1. Now the parameter, you have to specify what the parameter is. So let's just see what it is. And also it asks for the orientation, meaning which way is this thing going. So let's go ahead and you can put an arrow at t equals 1, it'll tell you which direction it is going, increasing t, which way it goes. And I think that's all we need to know. So obviously this is t equal 1, this was t equals 0. And so it's going in this direction. And if I were to modify increase t to something a little bit higher, to 2, and I said OK, you can see it gets longer. So increasing the parameter t increases it longer. Now, the interesting thing is if I go back and I go to a negative t, I get, let's say I go to -1, it's the same curve, and what happens is it retraces itself. So this is the actual curve, and if we went back to the original restrictions, I said x and y, x has to be greater than 0, and y has to be greater than 1. And you can see that there is no value of x less than 0, even though if we go back to our expression when we eliminated.
Recording started.
Okay, sorry about that. Pushed the wrong button. So when we eliminated the parameter, this didn't have any restriction on x or y. So x could be negative. But from our original parametric equation, we know that x has to be greater than 0, can't be less than 0. So you've always got to be very careful about that particular thing. So let me, we're going to stay in here, but I'm just going to take a quick trip over here, and I'm going to copy the result into the notes here. So, okay. So now I'm back. So let's add a page, and let me paste in that picture. So there it is. That's the curve. That's the parametric equation. This is the XY equation with this limited domain.
Recording started.
Okay, we're on problem number 10 section 10.2. So again, we can do eliminating the parameter in this case. And so what do? Well, I guess you could go either direction. First, we have to look at the domain of the original function. So we know that t has to be greater than 0, because if t is less than 0, then that does not exist. The fourth root of a negative number does not exist. Okay, so what does that say? So if this is greater than 0, x is going to be greater than 0. And if t is greater than 0, then y is going to be 3 greater than 3. Actually, it's going to be less than 3. So that should tell us something about what this plot should look like, especially when we do substitute it in here. So since we want to have y as a function of x, we just say y is equal to 3 minus t, but let's not do that yet. So we take this to the fourth power, so you get x to the fourth is equal to t. Because this is t to the 1/4 power, so if you take the fourth power, but you get t. And so when we substitute that in, we'll get y is equal to 3 minus x to the fourth. So again, looking at this function, it's a fourth order polynomial with a value of 3, and it points downward. So if we just plotted this, it would look something like 3 here, and then it would probably kind of look like that. Because it's fourth order, it has a little bit sharper look to it. But because of the original equation, we would not have this part of the curve. So it would just be the right-hand part of the curve. Okay, so that's it. Let's go look at the graphing program. So we're again doing a two-dimensional plot. The equation is a parametric equation. And what we have is t to the 1/4 power. So we take t to the quantity 1 divided by 4. So that's x, and y is equal to 3 minus t. Now let's do the parameter from 0 to 1 to see what this looks like. Put an arrow at t equals 1. So there it is. So this is t equals 0, t equals 1. And so it goes in that direction. So let's see what happens when we put a negative t in there. Okay, nothing really happens, and the programs kind of figure that out, that it can't. Actually, it leaves a little blank there. I think that's, well, let's see what happens. If I take it back out to 0, let's see if that, yeah, look at now, it goes back to 0 again. So apparently when you put something that's not in the limit, then it messes something up here. It goes wacko. now if we increase the parameter to 2, it's just going to make it longer. And if we keep increasing the parameter t, it's just going to show more of the curve. But it looks like a fourth order polynomial because it comes up here and it's fairly flat. The slope's 0, the concavity is 0, and so it looks different than a parabola does, but it does go downward. Okay, so that's it. Let's make a copy of that. Go back to Smartboard. Share the screen. Paste. Wrong one. So let's move that over there. Okay, so there you go. That's what it looks like. Okay, we're on problem 23. So we're supposed to graph this thing, and then we are supposed to do the same. So it's the same as the previous problems. We're supposed to eliminate the parameter. So let's take the first equation. The parameter in this case is theta. So we'll get is x minus 4 is equal to the cosine of theta. So the cosine of theta is equal to the arc cosine of x minus 4. So what we need is a sine of theta, so that you have to draw a triangle. So if this is, we'll call this alpha. So this term here is alpha. So if the cosine of alpha is x minus 4, then you have the adjacent over the hypotenuse. And if that's true, then this side is going to be what you have is you have, let's call this B, side B. You know, x minus 4 squared plus B squared is equal to 1 squared. Or B squared is equal to 1 minus x minus 4 squared. And therefore, B is equal to 1 minus the quantity x minus 4 squared, take the square root, plus or minus. So that's B. So when you want to find the sine of theta, you have to put it in terms of x. So the sine of theta, there's actually two ways of doing this. I just thought of the other way, which is a lot easier, I think. Yes, there is. Okay, so there's two ways of doing this. So the sine of theta is the opposite over the hypotenuse. And the opposite is the square root, plus minus the square root of 1 minus x minus 4 quantity squared divided by the hypotenuse, which is 1. So then we substitute that in here, so you get y is equal to minus 1 plus or minus the square root. Sine of theta is 1 minus the quantity x minus 1 squared. So we add 1 to both sides, we get y plus 1 is equal to plus or minus the square root of 1 minus x minus 1 squared. Square both sides, so you get y plus 1 squared is equal to 1 minus x minus 1 squared. Add that to both sides, you get x minus 1 squared plus y plus 1 squared is equal to 1. So that, what is that? That's a circle with radius 1 with the center at x equals 1, y equals negative 1. Okay, so that's what it is. Now the other way you can do this is use the Pythagorean identity. So let me just add a page. So you square both of these. So you get x, well actually we have to, actually did I make a mistake? X minus 4. Yeah, I did. I've got that X minus 4 here. This should be 4. I don't know what happened to the... Okay, so that's 4, that's 4, that's 4, that's 4. So this is X equals 4. I realized that when I got back here and thought about squaring these things. So you get X minus 4. So we subtract 4 from both sides. So you get X minus 4 equals cosine of theta. You get Y plus 1 equals the sine of theta. If you square both of those terms, if you square both of those, which is valid, they'll still be, if you square something, things are equal, the square will be equal. So you get X minus 4 squared is equal to the cosine squared of theta, and you get Y plus 1 squared equals the sine of theta, sine squared of theta. You add those two together, you get X minus 4 squared plus Y plus 1 squared is equal to sine squared theta plus cosine squared theta, and the trig identity says that's equal to 1, so you get X minus 4 squared plus Y plus 1 squared is equal to 1, which is the same result. Okay, so that's what it is. Either way you write it. So let us go to the graphing program. So we open up the 2D plot and we go to parametric equations. And the X was 4 plus 2 cosine of t. Doesn't really matter what variable we call it. And the second one is, just to make sure I'm doing the right problem here. Crap. I wrote it down wrong. Anyway, the basic idea is the same, so I'll let you figure it out, but I'm going to show you the, so I actually forgot the 2 here. So I did 4 cosine of t. Okay, and then we have negative 1 plus the sine of t. So those are the 2 parametric equations. You typically let it go between 0 and 2 pi, so I'm going to go from 0 to 6.28. And we'll put an arrow at t equals 1. So there it is. That's the graph. You got a circle at x equals 1, 4, y equals negative 1. Is that what we had before? Is that what I said? So you don't see what I'm doing, but I just want to make sure x equals 4, y equals negative 1. Yep. Has a radius of 1. So that worked out good. Let's copy that over, copy clipboard. So there it is. So our parametric form of the equation, which apparently I wrote down when I started wrong. I forgot the 2 right there. The only thing that would be different, if that was a 2, we'd end up with an ellipse instead of a circle. But everything else. So, you know, when you're over here, you would get, you would divide by 4. So you'd x minus 4 over 4, and you'd square it. So let's just do that to show you what would happen. The only difference is this would be, if this were 2, if I put a 2 there, then I would divide by 2 here. I would divide by 4 there. And so this would be divided by 4. And so we'd have an ellipse where the major axis would be along the x direction. And the minor axis would be along the y direction. Okay. So this is problem 26. So turn my little thingy on. Okay, so 26 is use a graphing utility to graph the curve represented by the parametric equations. indicate the orientation of the curve. Eliminate the parameter and write the corresponding rectangular equation. Okay, so 26. X equals the secant of theta, and y equals the tangent of theta. Let me just close something here. Close my mail. That's bothering me. Okay. So, what graphing utility? Well, you can use your calculator. In your calculator, you would actually have to plot x is equal to 1 over the cosine of theta, and tangent you can use. Okay. So if you do that, but we're actually going to use the graphing program. And as a consequence, I think I'm just going to share my entire desktop with you. And then I can go open up the graphing program. So just hold on a second. Don't go anywhere. Where's my graphing program? Yeah, there it is. And you can do parametric equations as well in here. You just have to use t as the variable. So in this case, the equation has theta, but theta is just a parameter, so it doesn't really matter. So what we'll say is, wait a second. Let's change it here. I'm trying to remember how this works. I haven't used it for a while. So let me see. Just go to help for a second. Always, if you get stuck, go to help. Well, I didn't even get. Okay, well, let's see what happens. Let's put x equals t and y equals 2t. See if that actually works or not. Okay, didn't like that. I'm pretty sure this thing did parametric equations. I thought actually maybe it doesn't do parametric equations. Okay. Well, I have another program which I can use to show you, since I don't have the calculator to do it, to put it on the screen. So it's a little program called WinPlot. And in this case, you can do a parametric equation. So you pick a two-dimensional plot, and you can use your calculator for this, so you can at least see what it looks like. And you choose equation, parametric, and so that's the parametric equation. So what we'll do is secant of t. Secant of t is f of t, which is x, and tangent of t is the y variable. Then you have to put the low and high values of t, and usually you just have to do at least from 0 to 2 pi. So 2 pi is about 6.3. So let's just go from 0 to 6.3. And I think that's all we need to do. So there we go. That's it. Okay. So it's a hyperbola. And we haven't talked about hyperbolas yet, but that's what it looks like. A hyperbola basically is this area in the middle where there's nothing happening, and then the curve goes out symmetrically from this point. Okay, so that's that is what that particular parametric equation looks like. If you're using your calculator, you would again use. Let's go back here, and what you would have. Just make sure I'm sharing this with you, which I am. Okay, sorry for all the confusion here. So if you were using your calculator, I'm going to just do it in my calculator to make sure everything's okay. So so the things we do is you go to y equals with it in the parametric form. So you have to enter both the x and y equation in terms of the parameter. And so I'd have 1 divided by the cosine of t, and then the second one would be the tangent of t, and that's my equations. And I go to window, and you'll see t minimum, we're going to put t minimum of 0, t maximum of 6.3, which is approximately 2 pi, and delta t step would be 0.1. Okay, and then we push graph. And let me just go to zoom standard. There we go. So if you do the standard zoom, you'll get the hyperbola. Okay. Now we have to eliminate the parameter. We never did do that. So if we eliminate the parameter, it's a little bit different because what we do is we would solve for theta. So let's use that one. So if you want to solve for theta, So what you would do is you start with this, x equals the secant of theta. You take the arc secant. Actually, let's rewrite that as cosine. So you'd have x is equal to 1 over the cosine of theta. Or the cosine of theta is equal to 1 over x. So if you take the reciprocal of that, you take the arc cosine of both sides. And so what we get is we get theta is equal to the arc cosine of 1 over x. So you draw a triangle like we did when we had trigonometric substitution. So we say this is theta, and theta is the angle whose cosine is 1 over x. Well, this is the adjacent over the hypotenuse, and therefore this side is going to be x squared minus 1, because you take x squared, this squared plus that squared equals that squared, or we could say this squared is equal to that squared plus that squared, and you can solve for that, and you'll get x squared minus 1. Okay, now what do we do? Well, then we can, so I think that might be one way of doing it. I think there's more than one way of doing this thing. But let me just, so let me think here. Yep. Okay, I'm going to show you the other approach, and then I'm going to go back and I can figure this out. A lot of times with these trig functions, you can just trig identities. So what we would do, one way of doing it would be, say, x squared is equal to the secant squared. We'd square both sides, and we do the same thing here. Y squared is equal to tangent squared of theta. And if we go back to the Pythagorean identity, and the one I remember is sine squared theta plus cosine squared theta equals 1. And so if we want to get the one involving the tangent, then we would divide everything by the cosine squared, so we have sine over cosine. So we divide everything by the same number, and this becomes the tangent squared of theta plus 1 is equal to the secant squared of theta. But we know that the secant squared is x squared, and we know the tangent squared is y squared, so we can make those substitutions. So we get y squared plus 1 is equal to x squared. And that is the corresponding rectangular equation, or we could write it as y squared minus x squared is equal to -1, or x squared minus y squared is equal to positive 1. That's the equation for a parabola when we get to chapter section 1. So that's one way. I'm trying to think if there's another way that we could have done this. So theta is the arc cosine of, so if we went over here and we said that y is equal to the tangent of theta, theta is the arc cosine of 1 over x. So the tangent of the angle whose cosine is 1 over x, what you do is you go to this triangle. The tangent is the opposite over adjacent. So the opposite side is the square root of x squared minus 1. And the adjacent side is 1. So you would say y is equal to the square root of x squared minus 1. If you square both sides, you get y squared is equal to x squared minus 1. And then if we add 1 to both sides and subtract y from both sides. Actually, that's good. Well, yeah, what are we going to do here? We're going to move that over there. Actually, let's move y squared over there. So when we move y squared to the right-hand side, it'll become negative. And when we move this to the other side, it'll become that. And then if I switch the two sides, I get that. So you can see there's two ways of doing it. And this is probably the one on the right is the one that's probably used more at the time. Just to try to take these and use some kind of Pythagorean identity. Okay. Okay, we're moving on to problem number 34. So this is 1034. So what it says is determine any differences between the curves of the parametric equations. Are the graphs the same? Are the orientations the same? Are the curves smooth? So we have four ways of writing the same, possibly the same curve in the xy space, but using different, I don't know why I put y there. So as we talked about in class, one thing about parametric equations, sometimes there's more than one way of writing a parametric equation. And in this case, we'll see that's true. Now, just like in the class, we said that sometimes the allowable values of t will not be the same because of the original equations. If we ended up using eliminating the parameter, we'd probably end up with the same equation, but you have to go back to the original description to make sure you get the domain right. So that's what we're going to do first. Is we're just going to look at the domains and see what allowable values of t there are, and what does that result in as far as the equation. So so here's the domain stuff. So theta can actually take on any value. So we should be able to, and what will happen is cosine and sine go from -1 to +1. So we should get the full variety of options as far as everything. So in this case, the parameter is theta, and theta really can go from -infinity to +infinity. In reality, we only have to really go from 0 to 2 pi, and we'll cover everything. If we go, outside of this range, it's going to retrace its steps, because the cosine of 0 is the same as the cosine of 2 pi, the same as the cosine of 4 pi. So now b, because we have a square root, this term has to be positive. So we have to say 4t squared minus 1 has to be greater than 0. 4t squared has to be greater than 1. T squared has to be greater than 1/4, or t has to be greater than 1/2. Make sure to do that all right. And you can see what happens if t is less than 1/2. This number becomes small enough that this becomes a negative expression. Now, the absolute value can take on any value. T can be any value. It just becomes positive. So that's the requirement here. So t is, well, the absolute value of t probably. Is that right? Yep, the absolute value of t is greater than 1/2. Another way of rewriting it is that you'd go, say t can go from -infinity to -1/2, or it can go from positive 1/2 to positive infinity. Okay, so that's B. Let's go to C. C, again, for one thing, t has to be greater than 0, greater than or equal to 0. And also, t has to be, let's see, 4 minus t has to be greater than 0. So t, if we add t to both sides, we'll get 4 has to be greater than t, or t has to be less than 4. Less than or equal to 4, actually. Again, you can look at this. If t is greater than 4, then this becomes negative. Okay, so that's the restrictions there. And for D, t can take on any value here. The other one is that 4 minus e to the 2t has to be greater than 0. So 4 has to be greater than e to the 2t. E to the 2t has to be less than 4. And then what you would do is you would take the natural log of both sides. So you'd have natural log of e to the 2t has to be less than 4. Less than e to the 4, natural log of 4. So you take the natural log of both sides. And that becomes 2t has to be less than the natural log of 4, because the natural log of e to something is something. And then we divide by 2, so we get t has to be less than, and see, what about equals to? I guess equals, yeah, put an equal sign in there. So t has to be less than the natural log of 4 over 2. So, yeah, just thinking if that's, yeah, if you had this negative, you know, if it was negative 100, you get e to the negative 200, which would end up being close to 0. So you're still okay. Okay, so let me go to the graphing program, and we will limit our domain to these cases. So the first one is 2 cosine theta, 2 sine theta. So I'm going to quit from here, and then I'm back to my plot. So it's 2-dimensional plot. I'm going to, actually what I'm going to do is I'm going to do all 4 of these, and we will look at them all as we go along here. So let me just open up them all one time. So hopefully I'm doing this right. I won't have any problems later on. That's not what I wanted. Okay, so we're going to start up here. And so this one will be the first equation. So let me just, equation, parametric. So the first equation I have is 2 cosine of t. And the next one is 2 sine of t. We go from 0 to 2 pi. We'll put in 3.6, and we'll say OK. And it should end up being a circle of radius 2, I think, at the origin. So there's your circle, radius 2. So we got that. OK. Let's go to the next one, which is, well, this will be B, because that's where it's oriented on there. OK, go to equation, parametric. And the equation is the square root of 4t squared minus 1 divided by the absolute value of t. Hopefully that one works out. I don't know about the formatting. 1 over t. And we said that, let's go back to our thing. We said t is greater than half and infinity. So what we'll do is we'll put a half in here, 0.5, and then we'll go to some big number like 100 and see what happens. So you see, as t goes to 100, this is going to approach 0. Okay. So is that correct? So you can see it's okay from t equals 0 to 100, and it kind of goes boom like that. I'm not sure why it did that. I thought it was supposed to be like half of a circle. So let's see if there's any way you can change the increment at all. And if you put 0 on there, let's just see what happens. Yeah, see it goes right there. So I think what's happening, I know what's happening. Okay, so let's not go to 100. We'll start from what was my number here? A half. Okay, so we go from 0.5, and let's go just up to 10, because that's what it's doing is it's breaking it down to a finite number of increments, and it bases it on the range. Okay, so you can see, there we go. Okay, so that's it. So it looks exactly like the original circle, except it's only this quadrant. Okay, let's go to the third one. Parametric equation, and the one, it's the square root of t is x, and y is equal to 4 minus t, square root of 4 minus t. And if we go back to our domain, t has to be less than or equal to 4. So we can go from -4 to +4, I think. So let's try that. So we'll go from -4 to +4, and we say OK. And again, we only get the first quadrant part. And if you change the, let's say we go to 10, what happens? Nothing really. Because what's happening if we go back here, if I let t equals 10, you'd have 4 minus 10, which would be -6. Square root of -6 is not a real number, so that doesn't work. Okay, so again, we just get this quadrant. And then the final one is this thing involving e to the x. So let's do that one. Equation, parametric equation. And we have negative square root of 4 minus e to the 2t. Minus square root of 4 minus e to the 2t, and y is equal to e to the t. And let's go back and look at our domain. We said that for that particular case, that t has to be less than the natural log of 4 over 2. Natural log of 4 over 2, let's see what that is in our calculator. Natural log of 4 divided by 2 is 0.693. So let's just go from negative 0.7 to positive 0.7 and graph that. So there you go. It's that second quadrant now instead. And that's because if you look at the equation, you can see that y, here we go, if you look at this, x can only be negative because the square root of something always has to be positive, and so x is negative. And you also see that y can only be positive. So x is negative, y is positive. That puts you in the second quadrant. And that's why it is. So if we review, kind of summarize what we have, is the first equation gives us a complete circle. All the other ones give us parts of a circle. They match up exactly over part of it, but not entirely. And if we were to do eliminating the parameter, we get the same equation for all of them. And therefore, and also another thing is that when you have parametric equations, they have a direction to them. So this one probably goes around like that. This one goes that direction. So this one's going counterclockwise. This one goes clockwise. This one may, these may have different directions. So that's something different about a parametric equation, is that not only does it have an x-y coordinate pair, but it also has a direction to it. Okay, now we're on problem number 46. 46, 48, and 50 are all writing the parametric form of circles, ellipses, and hyperbolas. And it's pretty easy. Actually, I'm just going to do all of them on one page because it's not that much different. So 46 says you have a circle, and you have a center at x equals -3, y equals 1, and you have a radius of equal to 3. And if you go up to problem number 40, you'll see that the form of a circle is x equals h plus r cosine theta, and y is equal to k plus r sine theta. Actually, that's the circle. Yeah, okay, that's fine. So r is the radius, and the center, this is the x coordinate, and this is the y coordinate. Because when theta equals 0, then x is equal to -3. So if you think about this, just qualitatively, here's your circle. So when theta equals 0, this part becomes 1. Cosine of 0 is 1. So you get h plus r. Actually, I'm drawing this at the center, so that's not probably that good. So let's do this again. So what you have is at some point x, here's your circle, has a radius. This is the x coordinate of the center. This is the y coordinate of the center. So what it's saying is when theta equals 0, which is this point, the x value is equal to h plus 1, the radius times 1. That gives you a total. And the y variable, sine of 0 is 0. So that goes to 0, and all you have is the k height. So that gives you that point. So that's how it works. So all you have to do is plug in the numbers. So x is equal to h, which is -3, plus r, which is 3, times the cosine of theta. And y is equal to the y coordinate of the center plus 3 sine theta. So that's the parametric form of the circle. If you were to write the xy coordinate, and we'll find this out when we go back, but it turns out it's going to be x plus 3 squared plus y minus 1 squared is equal to 9. That's the way a circle is in xy coordinates. So this is the radius squared, and then when this goes to 0 is when x is equal to 3. Yes, okay. Anyway, we'll come back to that. Okay, next problem, which is 48, an ellipse. So you go up to 41, and you see the ellipse is equal to, the parametric form of ellipse is x is equal to h plus a cosine theta, and y is equal to k plus b sine theta. So it's very similar to an ellipse, except you've got a and b instead of just r. But these are related to the some of the dimensions of an ellipse, which we really haven't talked about. So I'm trying to decide how I want to do that. Yep. I think we'll come back. I'm going to give you the answer, assuming that you're going to come back and do this later. I probably should have done section 1 to start with, but if you have an ellipse and there's a center for the ellipse, which is at coordinates HK. An ellipse has a shape like this. And you've got this dimension, and you've got that dimension. This is the major axis and the minor axis. This is equal to A, and this is B. The B is a smaller number in this case. And then you also have vertices, and the vertices are right here. So let's go back to section number 1. Actually, the focus. So actually, they gave us everything. So I'm getting confused myself. So they're giving you the vertices and the focus. Okay, yeah. So the vertices are going to be the distance A, and then the vertices has a distance from here, and there's a relationship between this distance and that distance and that distance. And the relationship is, so let's just write it out here. C squared is equal to A squared minus B squared. And A is the semi-minor axis, and B is the major axis. Actually, it's not semi-major, it's just the minor axis and the major axis. Okay, and C is the focus. So what we're given here is C, and we're given A. So we have to calculate B from that. So let's just write it down. Let me put another page up here. So we know that B is equal to 5. We know that C is equal to 4. And so A squared is equal to, oh, sorry, A is equal to 5. Let me get that right. A is equal to 5. C is equal to 4. We don't know what B is. So we can solve for B. B squared turns out to be A squared minus C squared. So B squared is 5 squared minus 4 squared. 25 minus 16, which is 9. So B squared equals 9. And B is equal to 3. Okay, so we have A. A is 5. B is 3. K and H and K are given in the problem. So the parametric form of this ellipse is also the center, because the y coordinates of the vertices and the foci are 0. It's going to be drawn like this. It's actually going to be centered at x equals 0. So these H and K in this particular case are 0. So it all just ends up being x is equal to A, which is 5 cosine theta, and y is equal to 3 sine theta. So that's the parametric form. And 49 is a very similar, or 50 is a similar situation. In that case, the relationship between the vertices and the foci are a little bit different. So we go back to chapter 8, section 1. You can see that C squared equals A squared plus B squared. And C is the foci, and A is the major. So what we're trying to do is find B again. And once we know B, we can just plug it into the equation. So this is problem number 50. Okay, so looking at the problem, this is 2, and this is 1. So b squared is equal to c squared minus a squared if we solve for b squared. So you get b squared is equal to 2 squared minus 1 squared, which is 4 minus 1, which is 3. And therefore b is equal to plus or minus the square root of 3. We'll use the plus version of it. So once we have a and b, and that, again, because of the fact that it's along, it's along the y-axis in this case, because we have 0.01 plus minus 1, and we have 0.0 plus minus 2, and so that's vertical. Again, it's going to be centered at x equals 0, y equals 0. And so for a hyperbola, the parametric equations are x is equal to h plus a secant theta, and y is equal to, this is from your book, page 717, problem number 42, b tangent of theta, so we use secant and tangent. And again, h equals 0 and k equals 0. And so we get x is equal to a, which is 1. So x is equal to secant of theta, and y is equal to b, which is the square root of 3 times the tangent of theta.